All right, here we go, part 3. Find the values of x and y that make both these things happen. So everything that looks parallel has to be parallel. All right, so we've got an angle marked here, and marked here. There's two with x in them and one with y in them. If we started writing equations with x's and y's right away, we wouldn't be able to get very far. So let's target. I'll use the highlighter so I don't have to make such big arcs here. Let's target this angle and this angle. These are supposed to be corresponding angles. They would be corresponding angles that would make, if you look at the transversal connection I was talking about before, there's the transversal connection. The other sides of those angles are here and here. So now I've got the H all figured out. The H here has bars parallel at K and M, so that would make those parallel. Let's get that out of the way. So I know these two angles are equal if they're supposed to be corresponding to make those parallel. So just by corresponding, I know 5x plus 30. This takes forever. I'll save your time. Just give me a second. Sorry, I know that's painful to watch. So yeah, 5x plus 30 equals 4x plus 48. Those are the corresponding angles. Corresponding angles are equal. And then do some algebra. And we see that x is 18. So if x is actually 18, I know that this angle is, I just put 18 in there for x. I find out that's 90 plus 30, which would be 120. Hopefully if I put 18 in for here, I would check that out and it would also turn out to be 120. All right, so both these angles are 120. That's great. Now I can kind of tackle this, because this isn't just stuff with x anymore. I can kind of replace that and say, I know it's actually 120. 120 and this angle, look where that 120 is, and where this angle is, so I'm drawing through the expression. Those angles, if you connect the dots here and realize that are at the transversal now we're talking about is this one. The other sides of those angles are here and here. So the parallels I'd be talking about now are J and L, which is good, because I've already established K and M being parallel because of this corresponding business. Now this is going to help me with getting the other ones to be parallel. Get that out of the way. So if these are consecutive interiors, they're not equal. They add to 180. So if this is 120, I know already that this one's going to be 60. That makes life a lot easier. So I just need to figure out what it is for. If I write faster, this isn't so painful. My handwriting is actually better. How about that? Hey, I look like I know what I'm doing. All right, so y is 5. Y being 5 will make that thing equal to 60. And life is good. Okay. We can take definitions, postulates, and theorems and properties and use these to establish and prove other theorems, just like the perpendicular transversal theorem. All right, so here's a theorem. I think it's going to be on your theorem sheet. I should have that for you in class. If not on Thursday, then I'll have it definitely on Monday. I hope I have it on Thursday. So this is another type of theorem you could use to prove things parallel or prove that these angles are congruent. But really, this is just a special case of corresponding if you look at this. Those two right angles where they're marked look like corresponding angles on parallels P and Q. So that's nothing really new information. It's kind of written here special for perpendiculars in case you wanted to use a fancy shortcut, but it's really nothing new. In a plane, if two lines are perpendicular to the same line, then they're parallel. Basically, that means they're parallel to each other. So you've got a line going through the plane, and you find out that some line is perpendicular to it, and you find out that another line is perpendicular to it. The big conclusion here is that those two things are going to be parallel. So it's like if you see this kind of situation with all right angles and an H bar, it means the two crossbars in the HR have to be parallel. And there's a converse to that. This is the converse of the first way, which was if the lines are parallel and there's a perpendicular at one, then it'll have to be perpendicular at the other. Again, they're all just fancy shortcuts for what I'm trying to say, corresponding anyway. So you could just use corresponding and everybody's happy. All right, here's another one. Oh yeah, these are pretty heavy. They're new postulates, and they remind me of the ones in Unit 1 where it's kind of like, oh, there's at least 3 points in a plane, and every 2 points are collinear, and they're very generic and very basic. These do lead, though, to the two constructions we're going to be doing later after the quiz. So that's why we're doing the constructions we're doing, because they speak to these. Given a line and a point not on the line, there exists exactly one line through the point that is parallel to the given line. Seems a little bit strange why they put that in there. I'll draw that in a second. And this one, if a line and a if you got a line and a point, not on the line, there's exactly one line parallel. Let me show you that in two different cases here. The first one was saying if you have a line, see how great that looks, and a point not on the line, the question is there such a thing as a parallel out here? Can I be sure that I can even draw a parallel out here, or does it mean that every line I draw through here would have to intersect, or is it possible I could draw two different ones that are going to be parallel? Since all your experience has been in Euclidean geometry, you probably have okay, I should have drawn faster. You probably have no qualms about the fact that there should be one parallel through here and that there's only one. There's not like two different intersecting ones that are both parallel. No, there's only one line parallel. Same kind of thing with perpendicular. Sorry, these are such wavy lines. If you start with this same information, a line and a point off the line, and I'm trying to make a perpendicular from here that goes perpendicular to this plane. First of all, such an animal does exist. There is a way to draw a perpendicular, and there can't be two different ones. It's not like I can draw another one here and say it's also perpendicular. There's only one that goes through there to make that perpendicular. So that's all that's really about. All right, these type of things, these two theorems here, the postulates, the parallel and the perpendicular postulate, they're good for constructions. They're not good for proofs. Let's get to proofs. Again, these are going to look a little easier when you have the theorem sheet in front of you. I don't know, there hasn't been that many new theorems, so maybe this won't be too bad. But I think all we have left on this sheet is just, two proofs. This is Unit 2. Yes, we are going to have proofs on the test, and they're going to be a lot like this one. So pay attention. All right, we're given that angle 1 is congruent to angle 2, and you know what? Let's go ahead and mark that. Angle 1 is congruent to angle 2, and angle 4, I'm going to mark it this way, is congruent to angle 5. So that's all it says at the first that's given. I know you want to say something about 2 and 5, just, easy there. All right, we'll get to that. And I'm trying to establish the fact that just knowing that stuff about those angles and the way this picture looks, I should be able to prove that RS is parallel to QP over here. All right, let's do this in order. It's going to take 4 steps to get there. That stuff, they told me, so I can just say given. You always put that at the top of the proof. What does vertical angles tell me? So remember, this column is the reasons for what I want to say, the facts kind of over here. Vertical angles is about what in this picture? Well, this is the thing I just said a second ago just to wait on, because now we're already ready for it here in step 2. It's angle 2 and angle 5. Those are vertical angles. Right now you're probably going, well, duh, why do I have to write that down? What is that good for helping me get here? Just wait a second. This is your first proof we've ever really done in homework. So we'll get to, you'll see when it's all done why it's in this order and why this was logical. But for now, this is nice. This is here for you. It says use vertical angles to say something. So vertical angles, where are the vertical angles in this picture? What does that have to do with anything? Well, it has to do with 2 and 5. So that's kind of nice. Now that I've said 2 and 5, let me remark these a different way. Let's mark 2 and 5 congruent. That's great. And so now I know anything congruent to 2 would be congruent to 5, and then, because they're all congruent to each other, which is exactly what transitive's for. So I need something, I need to use transitive somehow, and look at all this stuff I've got to work with. 1's congruent to 2, 2's congruent to 5, 5's congruent to 4. See how I did that in that order? 1's congruent to 2, 2's congruent to 5, 5's congruent to 4. So really all of them are congruent. Which ones are going to help me establish this PQ and RS? Well, we're hoping to get, wrong tool. We're hoping to get PQ parallel to RS. Is there any angles touching both of those? Yeah, one here, one here. Connect those. Connect those dots with their transversal. We have the H-bar stuff going on. I could make these a little bigger. Angle 1 and angle 4 are alternate interior angles. Write that down before I forget it. Alternate interior angles, angle 1 and angle 4. Okay, look at this thing as a group now. Now we were I think we were established up to this point. 1's congruent to 2, 2's congruent to 5, 5's congruent to 4. Therefore, 1 is congruent to 4, because they were all part of the same family where all the angles were congruent. I picked out 1 and 4 though because 1 and 4 are alternate interior angles on this Z shape, making RS parallel to QP. Because this says if the alternate interior angles are congruent, then the lines are parallel. Stop and rewind if you want to see that again. All right, here's a proof you got to do completely from scratch. You have this big, open, empty, scary space you got to fill in with all kinds of smart stuff that looks like this. All right. Given all this stuff, AB is perpendicular to BC. Let me just write that in here like this. ED is perpendicular to BC. Okay. ED bisects BEC. Oh, ED bisects angle BEC. Oh, yeah, okay. I was looking at the bottom. It's at the top, so those are the same. Let me write down the obvious facts from that. Oh, first of all, I have to put all this stuff in here at the given, right? Remember? This is how proofs work. You put that stuff in there as given, and at the end, you put what you're trying to prove. So I know this is just how proofs have to go. I just copy the problem here. All this stuff. Oh, I wish I could copy paste, but this is one picture. It's not going to work. All right. I'll pause and do it, though. Okay, so all that stuff, I just recopied this down here and said, yeah, that's given. Okay, then it's kind of like, well, so what? And how do we use that to logically string together a if, then, if, then, if, then to get to this as a then sometime? And I have no idea right now what that reason is going to be. I marked this 2 congruent to 3, but I should probably list why I was able to do that. Angle 2 is congruent to angle 3. Oh, good. I'm talking about angle 3. That's good. I want to be talking about angle 3. Why do I know those are congruent? Well, I just went ahead and marked those as soon as I saw the word bisector. So this is definition of angle bisector. Because it's a bisector, I know I can do that. Perpendiculars I just marked, and that's exactly what it says. There's really no justification for that because that's what that means. But knowing that those 2 angles are different is technically kind of worded differently than saying this word bisector. Now I'm actually talking about angle 2 and angle 3. And again, that's good because we see angle 3 coming up. All right, I'm supposed to talk about angle 1. Angle 1 congruent to angle 3, and this chapter's about parallels, so kind of what's going on? Well, I got 2 lines here, AB and ED, both perpendicular to the same line. If you're stuck on what to do in these proofs, and it's going to happen, look at what you're given. And we got to make sure we sort of harvest all the truth out of this and use it to transform into some other truth so we can use it for something. AB and ED are both perpendicular to this same line BC. And we just learned a couple pages ago, well, pages for me, that if 2 lines are perpendicular to the same line, then they're parallel to each other. Again, it's a fancy version of corresponding. So you could say corresponding, or you could say that fancy thing. I'm going to say corresponding because I don't want to keep track of all those other little theorems. By corresponding, then, I know that, oh, I'm not going to have enough space, that, okay, both these things are perpendicular to the same, so here's the transversal. AB is actually parallel to ED. If that's true, I think I could do it in 5 steps. If AB and ED are parallel, let's mark that. Great, those are parallel. Because I want to say something about angle 1. Well, look at these parallels here. I could have done this sooner, I guess. If these are parallel, and I want to say something about angle 1, so I'll highlight the side of angle 1. 1 and 2 are connected as AIAs. They're alternate interior angles. Alternate interior, now that I know AB and ED are parallel, I can say 1's congruent to 2. Running out of space. 1's congruent to 2 because of alternate interior. Now look at the list here. I've got 1 congruent to 2. Oh, good, I said something about 1. 2's congruent to 3. Oh, good, I said something about 3. Look at that. Angle 1 congruent to angle 2, and angle 2 is congruent to angle 3. So why is angle 1 congruent to angle 3? Textbook example of transitive. That was probably really hard to follow. Rewind a couple minutes and watch that again, and I will see you in class.